Recording started.
Alright, so we've got to get through a lot of material here, so let's get started. The first thing we're going to do is talk about a vector, and a vector is simply a direction and a magnitude. The direction you can think of as the direction the little arrow points. The magnitude you can think of as the length of the little arrow. We're going to call the start here of my array the initial point. So I could have vectors going off in different directions. Here's another one going in a different direction. I have all kinds of different vectors. Now, what we're going to do to standardize these is make them what are known as position vectors. So if I think of the XY axis, here's the X, here's the Y, and I have a position vector, which means I have a vector whose initial point is the origin. It goes out some direction to a second point. And let's say the coordinates of the second point are 2, 3. What we'll do is we'll say that in a vector in this standard position, we'll call it vector v, is going to be the vector 2, 3 with those strange parentheses. Anytime you see these strange parentheses, you know it's in standard position, and it's just a vector whose initial point is on the origin. The magnitude, of course, the magnitude is the length of the vector, and the magnitude is given by these weird little braces here. It's like double absolute value sign. But it's just the square root of a sub 1 squared plus a sub 2 squared. So for example, if our vector v is the vector 2, 3 from the previous example, then the magnitude or length of our vector v is the square root of 2 squared plus 3 squared, which turns out to be the square root of 13. So that is the magnitude of our vector. Vectors can be thought of, or can be thought to be made up of, vertical and horizontal components. So again, if I had a vector, so I had this vector, and that's the vector 2, 3 again. It could be thought of as being made up of a horizontal component and a vertical component. Yellow doesn't show up that well, and of course the horizontal and vertical component are given here, but the magnitude times the cosine and the magnitude times the sine to get to the vertical. Vector addition. Now they'll give you some formulas in the book for vector addition, but let's just do a concrete example. Let's say I have vector v, and vector v is 2, 3, the same vector we've been dealing with. Let's do a second vector, say vector b. Vector b is the vector in standard position -3, 5. If I wanted to add these two vectors, vector b and a vector b, all I do is add the first components and then add the second component. So I'm going to take 2 plus a -3, 3 plus 5. So vector v plus b is the vector -1, 8. Vector subtraction works essentially the same way. Again, I'll just get us two vectors. Vector B is 2, 3. Vector B is the vector -3, 5. And if you want to subtract these two vectors, you just subtract the individual components. It's going to be a new vector, but it'll be 2 minus 3, comma, 3 minus 5. Of course, these two minuses will combine together to be 1 plus, right? So I'll get the vector v minus b is equal to the vector of 5, comma, -2. And that's vector subtraction. Scalar multiplication, first things first, a scalar is just a regular number. It just has the one component, the value. So what we're talking about is multiplying a plain number times a vector. So again, if I had vector v and that was going to be 2, 3, the same vector we've been dealing with, and I had some scalar number, say 5. If I want to multiply those, k times b, I just multiply 5 times each component of the vector. So 5 times 2, comma, and 5 times 3. So the scalar multiplication k times b is the vector 10, comma, 15. Essentially what you're doing is just lengthening this vector. When you multiply it by a scalar, you're just going to lengthen it, and unless it's negative, in which case you can reverse this direction. Dot product. All right, the dot product is a weird little operation. It's not like multiplication. The dot product of two vectors gives you a scalar number. It does not give you a vector. It gives you just a regular old number. You can see the formula here, but let's just work a concrete example. If I have the vector v is, again, I'll use the same one I've been using, 2, 3, and the vector b is -3, 5. The dot product between v and b will be, let's see, a sub 1, that's 2 times -3 plus 3 times 5. So the dot product between v and b will be -6 plus 15, which gives us a plain old 9. And remember again, the dot product, the answer to a dot product, is not another vector. It is a plain scalar number.